To talk about work with Mark Braverman, Anup Rao, and Ran Raz. And it's about constructing pseudo-random generators for branching programs that will be regular as well. So I'll start by just definitions and some history. This has been considered, and I will try to give the all the details of the proof, or at least the parts that are new in this type of in this work. So what is a branching program? It's a graph that has n layers, v1 to vn. In each layer, we will have d vertices. So here these 4. And we want this graph to compute something. So every vertex here has 2 outgoing edges. And one of them is labeled 0 and one of them is labeled 1. And then every string with n-1 bits defines a path in this graph where we will start the path here. Let's say it's the vertex 1, 1. So x, from 1, 1, we use x to get to some vertex in the last layer. So every x take us from this vertex somehow to this. So this is a computational model we will consider, and this model sort of represents a computation where the space is bounded by some function of d. So at every step we remember only d things. And another thing, so the space is bounded, and also it's a read once computation, because every time we do a step in the computation, we read a new bit. So we don't read no bit twice. So these are branching programs. And this d is called the width of the branching program. Okay, this is well known. And now we will try to fool these objects, to construct pseudo-random generators. What does it mean to fool?
How different are the models when one is allowed to read only once and many times?
Very different.
No, it's very, like for this kind of, like for the randomizing log space, the read once is what you think about, right?
Yes, for log space.
Because that's the way the access you have to the random tape.
The standard log space machine can read the input anytime. Right. And we don't know that this one doesn't. But this read once model is a computational model, it's much weaker. But
No, but the access to the random tape.
The access to the random tape in log space machine is one way. So once you fix the input, you can just try to pull this model.
Okay. And we will, so yeah, we want to fool them. What will I mean to fool in this case? So we want to construct, so in general, a distribution d on 0, 1 to the n-1. Epsilon full, and here will be length n, width d branching program if so for every branching program b of length n and width d, such graph, so I'll explain what is written here. So this denotes the uniform distribution on this cube. This will be the distribution that we consider. Each one of them defines a distribution on the last layer of this graph. How do this is this distribution and this distribution? How is it defined? We choose x according to d, and then the value is b of x. So this is b of x, this value. So we want these two distributions to be statistically close. So we choose x according to the uniform. We get some distribution here. We want d to have sort of the same distribution on the last layer. So this is what I mean by fooling. And what we want to do is to construct d with minimal support. This is the goal we are trying to achieve. And yeah, to like construct is like efficiently. And why do we want to achieve this? This is a way to, so everybody I guess know this, but this is a way to de-randomize algorithms. If the support is small, then the running time will be, we can go over all strings in this support in time 2 to the support, roughly. In times the support, yes, sorry. And by doing so, we can sort of check if we get here or not, or like various questions of this form. So this is the goal, and this. So if I'm misstating history, please.
So can I say one more time? What do you mean d with minimal support? What do you mean by support?
Support of a distribution is all the.
Oh, just okay. I see.
So.
The signal D is the output of some pseudorandom generator. So you want to have small c.
Right. Okay. Ideally, you would like D to be log space computed, not like the only time would be.
Yes.
And every step in the definition, every step depends on i's x and i's d, right? Yeah. Like x sub I and d sub I, every step in your branching program.
What is d sub I?
I's bit of capital D of the seed.
So I think you think of capital T as giving each xi a value.
Okay.
So it's not clear what is written here. So here, this distribution is, we choose x from D, and the value is b of x. Okay, so this was considered in many places. I think that the first such question was suggested and solved, or just solved. Do you know? I like.
Well,
BNS
BNS
before that.
yeah.
So I. Yeah.
Yeah, definitely. DNS had a different one. Baba instance had a different.
So.
Yeah, maybe you should mention that just the existence of a D with polynomial support is easy
Yeah.
counting argument.
think the question was around, well, before VNS. I mean, just people were wondering it.
Yeah, no,
Yeah,
that's a
so
different.
but
Probably
no
by
one had
since
thought
I-
that.
Yes.
That's
And
the
you
first,
need
these
that
are the
kind of
first
portion.
solutions.
Yeah.
So
Trivial term.
what
Years, how do you put it?
what
Years.
90
88,
89 or VNS 88 maybe.
So what did Noam proved? He constructed D log support of D is something like log n log D plus log n plus log 1 over epsilon. Let's put everything up to constants. So this is what Noam did. He constructed such a distribution in a very explicit way, whose log of its support is almost as small as it can be. So we want, this is, without this log factor, this is sort of the best possible, and he missed it by a log factor. And then arguments of this form, or variants on this argument, were then by Noam and Nissan and Zuckerman, and then Nissan, it's this paper,
But I comes before.
I end.
Trying for unity there.
Yes.
But really, okay, these results, the generalized it beyond branching programs, but for branching programs we didn't get anything new.
Yeah, but it's I think about the important thing about the Nissan Zuckerman paper, and also to some extent in ours is using extractors instead of hash functions, which are more costly. Well, in some cases it looks like you could save something.
So this was what was known, and
This is where extractors kind of were defined.
In Nissan Zuckerman extractors were the formal.
So they were defined inspired by this construction.
Yeah, so the idea in Nissan Zuckerman, the parameters were different. So what Amir will concentrate on, and most attacks concentrated on D small and N large. I would add AKS there actually before Nissan Zuckerman. And what AKS and Nissan Zuckerman concentrated on is D large and N small. So what they said is we want to full probabilistic log space computation. For how much time can we fool that? So if the time is log n, you can fly. I mean, if the length of n is log n, you can fly with possibility. And they showed that you can do polylog n with a polynomial support distribution. Right? So that it was a different trade-off. But anyway, extractors came in the game really because of one reason was this.
What's the connection between this question of your randomizing log space? Is there a correspondence?
Yeah.
so
So log space is when D is polynomial. Yeah, that's it.
and you also have the, which I'm not sure how to use, but you have that this comes from a Turing machine, so it's not a general graph.
Okay, but
Yeah.
non-uniform log
Yes.
space is exactly
Yes.
what people try to de-randomize.
Yeah.
So
When you say polynomial support, it's like the counting thing gives you something like n times d divided by epsilon or something like that? Or
Yeah.
it's
And
Yeah, it's the size divided by
yeah, yeah, if you just ignore this, then. So okay, so this was the history, and here we'll construct such things with a bit smaller support, but only for regular branching programs. So I'll just now say,
Are you going to mention epsilon bias because that's part of the history?
and I didn't plan to.
Well, but that will be anyway. You'll use a special case, which is the regular branching programs, right? So very special case of
Yeah, it's
regular
yes.
branching programs is when these two. Oh, you're
Yes.
going to talk about groups.
No, I didn't. I wanted to. No, I didn't want to talk about groups, but I can talk about groups. It's,
Well, just
Yeah.
mention it's a special case, probably
Yes.
interesting for some people here. But what? Yeah.
Yeah,
Well,
so-
define
yeah.
regular.
So what is a regular branching program? It's exactly the same thing, but we have one more condition, and the condition is that the integrity of every gate, of every vertex in this graph is also 2. So this is regular, and a special case of regular branching program is when it's a permutation branching program, where the edges that are labeled 0 in every layer are a permutation, and the edges that are labeled 1 are a permutation. So regular are a bit more general than permutation because we can have 2 edges labeled 1 going to the same vertex.
It's the same regularity at every layer or different regularity in each layer?
No, it's 2 throughout.
Wow.
Yes.
So if it's a 2 regular and throughout, doesn't it like mean that sort of very quickly somehow converges?
So maybe something. So a special example of regular branching programs is when this graph represents a group of size D. For example, if D is 2, it represents the Boolean Q. And then you want to construct for D equal to an epsilon biased set. This is exactly an epsilon biased set. And even to construct, that's, yeah, that's a,
No, but I mean, when you have regularity more than 1,
No, but permutation is a special case of regular.
yeah, but I'm just trying to understand when, like, regular, if you have regularity more than 1, then don't you have
Permutation is regularity too,
I'm not sure.
because there are 2 in, 2 out going, and 2 in going.
So what's the definition? So regularity means like, okay, so
2 in, the integrity is 2.
the in degree is 2.
Yeah,
Ah,
it
okay.
says that in their definition of regularity, you don't need consistent labeling in the regular.
Yes.
Their generator works even if it's inconsistent with it.
So, okay, so you don't need. So you do think of regular in the sense that there is just the in degree is 2 and the in degree is 2. There is, but it will be 2 ones rather than 1 0
Yes.
and 1 1.
Mhm. Yes.
I think probably it's better to write specifically what the group thing is. So the regular branching program for groups is just a word in the,
Yeah,
in the
so-
group G1 up to Gn.
So an example of a regular branching program is we have a group G of size D, a finite group, and this program will be defined by a choice of G1 to Gn minus 1 in this group. And these tests, these 2 distributions, will be of the form, so we'll have x in 0, 1 to the n minus 1, n minus 1. This x will, using these, will define a function on G. So we'll have G1 to x1, G2 to x2, to Gn minus 1 to xn minus 1. This is another group element. So every x defines a group element. And now when we choose a distribution on x, we get a distribution on the group. This is a distribution. And we will want these 2 distributions to be similar. So we want to be close to the case where x is uniform using some other much smaller distribution.
If G is Z2, then this is just fooling all linear tests model.
In general, like this is the trade-off, like this trade-off you want now, that's the optimal because neither of these terms are supposed to be multiplied by log n, right?
No,
Not
you don't. Yeah,
No,
you don't want the
this
log
is-
n.
No, I mean what's known. I mean like neither of these terms, like neither log d, not the other log n, nor none of them is known how to be taken out of that log n. Like not even like the epsilon.
No.
I don't think so.
No, not in this setting. There are other settings where you have like combinatorial rectangles where you can do this. but
Because you
not-
could hopefully to improve it at least, take the log D or the log A,
Is anything known about the power of regular Latin programs versus general?
Yeah,
For large,
I don't
for
know.
large D, I guess for constant D it's the same, but for large D.
Why for
The power
It's
of
not
the power
clear.
of
I don't know.
Just by Darrington's, I would guess that for constant D it's the same.
for F? Well,
Ah,
so you're talking about read once or general?
yeah.
Read once you cannot do anything computationally, really. Barrington doesn't work.
Right, but for example, if I looked at a log space, randomized log space computation as a read once branching program over the randomness,
Yeah.
it wouldn't be regular. And if I restricted it to regular, would I get something different?
It seems that if you could prove them the same, then the results of Omer and Salil and Luca, etc., would work. So, right, I mean, they have
Oh,
generalization for
they also
SL
have
and for regular RL. Some
not
version of
constant.
regular.
There is not consistent labeling
Consistent
issue.
label,
Yeah,
it's
so
a
it's-
form of regular.
Yeah.
It's consistent labeling.
So okay.
So, Doc, what is the difference between consistent labeling and not
Doesn't
consistent?
matter.
Let's. Yeah, we are going in like.
Okay.
Okay, so I just want. There is a nice idea, I think, somewhere
Can you
inside.
summarize
So.
the history of complexity theory?
So there was a small point somewhere in space, and then it blew up, and okay. So what we do here is do we epsilon full, but only regular. And the log of the support, so we construct an explicit in the same spirit of all of this. So the only difference here is this log becomes log-log. And yeah, it's a big difference. We would be very happy to get rid of this. Then it would be a polynomial for constant width. And we don't know such things. But here we get, instead of n to the log n, we get n to the log n for constant width. Yes, so this is what I'll try to explain. So it's clear what
By the way, I guess you can always think of 1 over epsilon as larger than, as smaller than D or something, so the log 1 version will be the distribution is only over D terms.
So you can still want to
Yeah.
do 1% error with D, which is large. You could.
No, I mean, I'm just saying you pay with this log D, so that's what I mean, that you can think of 1 over epsilon as smaller than D.
Anyway, the whole problem, maybe you didn't say it because there are too many parameters. Nobody could beat log n squared, even for constant D and constant epsilon. There was no way to beat log n squared until this one.
So I'll explain the long proof. I hope you will appreciate it at the end. This can be proved like in a page. This works, and I will try to make it longer to give some story, intuitions. So I want to start with a different question. So I'll denote by binomial with alpha. So this will be a distribution on 0, 1 to the n minus 1.
Why are you switching from n to n minus 1?
I'm not sure. That's a good question.
We allow you
Yeah.
to use them.
So
No, okay, so then you have
so let's. Okay, so and this will be xi will be 1 with probability 1/2 with, let's write it, with this will be 1/2 plus minus alpha. So what is written here is that every xi in this distribution is almost 1, is equal to 1 with probability almost 1/2, and these are independent. So it's a very, very a distribution with a lot of randomness in it. Every
Family of distribution?
yeah, so it's a family. Yeah.
It can also be that each one is exactly half.
Yes. So yeah, this will be the convex body of such distributions. But you can think about each one being exactly alpha. It doesn't really matter how we think about it. Okay, and the first question we'll try to answer is, for which alpha does this work? Okay.
xi equals 1 is inside the interval plus minus.
So this is the question. And what we'll see, so, and what I want to say, so the statement I want to,
Do you want the D on the top or on the bottom? It seemed like it should get worse.
you're right, yes, D to D, yes. So this is the first statement I want to prove, and what does this tell us? It doesn't tell us almost anything. It tells us that if these are, so let's think of epsilon and D as constants. If every bit here is a constant close to uniform, then this works. And the proof of this statement will give us like the main idea in the proof later on. So how would we prove this? We'll use a hybrid argument. So it's, what is a hybrid argument? We have our distribution, this distribution, and on the other hand we have the uniform distribution. And we want to be able to relate the error here to the error here. So the hybrid argument gives us a way to relate this. So we'll define this to be dn, and then we'll define dn minus 1. I hope that I'm not confusing the. We'll define a sequence of distributions. We start, the first one will be, or last one will be this one, and the first one will be this one, and we'll use this simple inequality. So it's clear what is written here. This is statistical distance. Because it's a norm, we can do this. So yeah, so this is what we'll do. And now it remains to define this distribution, and we do it in a very standard way. So we'll have, so in this construction, we'll choose x from and u from un. So these two strings will be we'll choose this independently from this. And then we'll define one distribution that starts with x and ends with u. This will be all of this distribution, and the only difference will be at the position where they switch between x and u. So d sub I will be x1 to xi, and then u I plus 1 to un.
This is the theorem for branching for regular branching programs, right?
Yeah.
This is a theorem for regular branching programs.
So
Yes.
the difference is that usually you have in a hybrid argument, you have a uniform bound on the other side. You just take the worst case, and then you multiply by the number as a way to bound the sum. But here, you're going to have to be
Yeah,
not,
not that far.
so basically,
because already
what you
the
have to
first
show
layer-
is that this difference basically decreases exponentially
Converging.
with n minus I or with I.
No,
That's
it will be it will be clear how I will do it, but it's not. It will be clear.
Converging sum because the first term already gives you a constant.
There will be no convergence. You will see.
Is this somehow motivated by the variance that you use this perturbation that you have in the binomial?
Um,
Seems very similar.
No,
I don't see it, but maybe you can view. I don't.
no, I don't think that since they made it.
Because it seems like we're doing some noise in the Boolean calculation.
No, it's not. This error comes naturally from the construction. It's not. It's not something induced like in the uses of invariant specifier. At least I don't see it. But you can say later.
Okay. So now we'll bound each term of these by some other quantity, which I will define. So what is this quantity? So we have this branching program, and we have x and u. So we have these x and u.
So you want to look at pairs of states
So
that you could reach at level I plus 1 and look at the difference in the uniform distribution starting at those states.
So I'm not sure that I follow, but so we have d plus 1, di plus 1 goes with I plus till the I plus 1 bit according to x, and di goes to I according to x. So we have these two layers. And now we will bound this by first conditioning on the place here that we reached. So we'll have. So I'll try. There isn't much room, so I'll write it concisely. But we go over vertices in this layer. We have the probability of reaching this vertex according to D, to the binomial alpha distribution. So these walked exactly the same path up until that point. And now we'll multiply by what could be the difference. So for this, I'll denote P of V to be the probability over the uniform distribution that from V, let's say, we reach accept. So we reach that vertex, for example. So now what do we need to multiply it? So di, what does it do? With probability 1/2, it goes, so
Some U0 and probably a half it goes to U1.
yeah, so let's see what happens here. We have V, and there is an edge going to V1 and an edge going to V0. So with probability 1/2 we'll have P of V0, and with probability 1/2 we'll have P of V1. So this is
So can you write the 1/2? It's the field. Yeah.
And in the other case, it's a half plus alpha, half minus alpha.
yes, and in the other case is 1/2 plus, let's say, alpha I P of V1.
Sigo it as the same alpha everywhere, probably it doesn't matter.
So the difference is the most alpha times the difference between the distribution under the uniform distribution starting at V0 and starting at V1.
Yes.
So
Alpha I.
Doesn't matter if it's the same alpha.
so that's, yeah, the most alpha. But since we're summing, yeah, up all those are just going to sum up to 1. So it's bounded by alpha times the maximum.
So I will do a uniform bound indeed. We'll take, so now I just wrote this to point at the fact that we don't need alpha I to be alpha. They can vary on whatever value we want them to be, irrelevant of the other positions. And also they sort of can depend on this position. This doesn't hurt the argument. So we will not use it, but maybe it can be useful.
But it's the same alpha I once. I mean, alpha I is defined, right?
It can be alpha V, you were saying. It could be
Yeah, it
alpha
could even be alpha of I and V.
I see.
So, but it's not. I will not use it. I just wanted to sort of point at this. But we'll bound this by alpha times sum over V, this delta of V.
You want to use it later? The expect alpha independently, it's not what we
No.
use later.
No.
So the delta of V.
So we'll see what. Okay, so this is what we did so far. We bounded this error. So now this is in VI, and the total error.
What is the probability? Includes the probability of reaching V or
Yes.
No, no,
I know.
just this.
No, so you so you bound so you
I
need to bound
just-
it by that. You have to multiply this by the probability of reaching the.
Which is at most 1. So
You are using.
so I'm doing the stupidest thing that you can.
Are you willing to lose a factor of D?
Yeah, it doesn't really matter for us. So this is alpha times sum over all vertices now, all this number. So this is what we got so far, and now will be the point where we. So this was a general statement. We didn't say. We sort of didn't use any property of the branching program. But the theorem is that for regular, this is at most 2D. So this will be what I'll explain next.
It's like you're taking a random log on this graph.
Mm-hmm. Yes. Okay. So now I want to argue this theorem. So the proof it will be sort of we'll play a game. So we'll have 2 steps to the proof. The first one is that, so we'll have some pebble game, which I will define. And the first one will be, it's a sum is at most the gain in some game. And then we'll show that the gain in such game is at most 2D. There will be two different. It's one way to argue. It's not the way to argue, but I think it's nice. So what will be the gain? So the gain will have 2D pebbles. So let's write Q. So these will be just numbers between 0 and 1. We can think about them. There is this line, and there are these pebbles on this line.
The line is 0 to 1.
Yes. And the moves in the game will be the following moves. We choose QI and QJ. So this is QI and QJ. And the move we'll do is move both of them to the middle. So move to QI plus QJ over 2, both of them. And the gain will be PI minus PJ. So if we can, so we can move pebbles one towards the other, and then if they're far away, we get a big gain, and then we want to maximize our gain.
In any finite number of steps.
So
Yeah.
what you're doing is you're thinking of, let's build the pebble game in reverse,
Mm-hmm.
you know, in a way that maximizes, and we want to say maximizes the sum, right?
Yes.
So now, the only thing, once we built levels, I'm n minus I through n, the only thing that matters about the previous construction is for each state at level n minus I, what's its probability of acceptance from then on.
Mm-hmm.
And so then we're trying to say, okay, now we're going to define which states at level n minus I minus 1 go to the same state.
So
So yeah, I guess
It will
nothing
be-
is proving step 1.
yeah, so this is sort of this argument, and I will do it. So indeed, before, these two steps have simple proofs, but is it clear what is the game? We move pebbles.
So the game is basically you want to place the cues in the most advantageous way, and then you have as much time as you want. And
No, so the start position is given to you.
Right, I mean,
So someone places the pebbles in the beginning. Then it hands them
you
to
want
you.
to say that the game is at most 2D no matter what placement, right? Or
No, so it will be very clear.
In the beginning, they're just going to be zeros and ones.
Yes, so I think it will be clear. So let's do first step.
It ends when all the pebbles are together.
Yeah, for
Might
example,
as well, yeah.
yeah, then you
Then
have
you'll
no
get
more
any-
gain. But you could have, I think, games that go on forever. That you never, it's very like 0, half, 1. So you like,
Yeah.
yeah.
And then
If you
go
just
infinite.
map zeros to, if you pair you start with 2 zeros and 2 ones, and you keep on pairing the 2 zeros and the 2 ones, then you'll get 2 zeros and 2 ones, and you can just repeat that, but it's going to be you'll have 0 profit throughout.
Yeah, for
Point-
example.
The point is that when you take a profit at one point, then you make the values closer together, and you reduce your profit. Now I'm trying to prove part
Yeah,
2.
so okay, let's start with 1, which is indeed a very simple statement. So we have this program. We have this program. We want to bound this, and we want to define by this program again. So as there, I will just consider the probability of hitting this vertex, although it doesn't really matter.
I mean, if you want, what you really are talking about is in the definition of statistical distance, a distinguisher, like you're saying the probability of hitting some set.
Yeah, but it doesn't matter.
Yeah,
Might as
so-
well be this.
I mean,
Yeah.
if he's trying to prove.
It doesn't matter.
There is a
Yeah,
factor
once
of
you
the.
prove this, you prove that way.
Yeah, it's so.
Are you losing a factor?
You don't need to lose, but let's.
Would have talked
Okay.
about
Yeah.
the set.
So let's. So how will we start the game from the program? We'll place Q1 and Q2 on 1, and Q3 to Q2D on 0. So we have 2 pebbles. We have 2 pebbles at 1 and 2D minus 1 pebbles on 0. This will be, so, and now we'll play the game. What will be the game? From every vertex, we has 2 edges going inward, and we'll view these edges as going backward. This is where we'll use regularity. So we will have, at every step of the game, we'll have 2 pebbles on a vertex. So in the beginning, there are 2 pebbles here. There are 2 pebbles on this vertex, 2 pebbles on this vertex, and 2 pebbles on this vertex. So every step will have 2 pebbles on every vertex. And now we will move these 2 pebbles, 1 to here and 1 to here. Okay, and these 2 pebbles will move 1 to here. Move the pebbles, and every step when we move 2 pebbles to one position using this program, the gain we get is exactly the difference between these 2 Qs. So what this idea shows us is exactly step 1. The sum over all differences along V's, this delta V's is, so this, if we play this game using this program, we get this gain. We can maybe get a larger gain, but this is,
Starting position corresponds to what?
so we place 2 positions on 2
Yeah,
pebbles on 1.
But what's the meaning of what an intuition behind this?
Because here on the lex, so we want to have this property. Qi, if it's placed on a vertex V, then P of V is equal to Qi. P of this vertex is 1, so we have this property. The P's of all of these vertices is 0, so we also have this property when we start. And because we play this game using these rules, we maintain this property.
Basically, a way of proving it by backward induction on the number of layers.
Yes. Okay. So now we'll do step 2. So for every, so well, the proof will be that the gain with this is at most some function which will be sum over I smaller than j qi minus qj. So we'll have some upper bound on the gain.
Well, this is the starting position.
So yeah, this will be the starting position of the game. And for every state in the game, we have L that corresponds to this state. So we will have L of start, then so L of 0, then we'll have L of 1, then we'll have L of 2, and so on. Every step of the game. Yes, it's a potential function.
That sort of immediately says that this square bound is like immediate.
This squared is immediate, and because of the starting position, D is the correct bound. but it's not that important. So okay, so I didn't complete so we'll have these L's, and we'll have two properties. First, by definition, every Li is more than 0. It's not. And the second property is that Li, so in the I step of the game, this quantity decreases by at least the gain.
So you just have to show one step where you combine Qi and Qj.
Yes. So this is very like just by definition. And how do we prove this? This step. So maybe I will. This step. This step, we move two pebbles, Qi and Qj, to the same position. So let's see what happens in this sum. There are two sort of parts of the sum. We have the part of the sum that involves some. This is not good. So we have Q primes that are not Qi or Qj. And how do they contribute to this sum? So in Lk, we will have Q prime minus Qi plus Q prime minus Qj. This is a quantity before we start. And after we do the step, we have Q prime minus Qi plus Qj over 2. This is the position of the new pebble, but we have two pebbles there. So we have this 2. And the statement is that this is at least this.
You have to add the gain. This is just the
Yeah.
position.
No.
This is a statement about this Q prime.
Then Qi and Qj themselves go from the gain to 0.
That's fine.
Yes.
So that's
That's fine.
So how does this follow? There are a few.
bigger than both of them.
Yeah.
then it's the
So
same. If
I
they're
will
smaller
just.
than both of them, then
I mean,
it's
this
the
is
same.
triangle
And
inequality.
if it's the middle,
This is convexity of absolute
Complexity of
value.
norm. It's like think of
So-
Q prime equals 0 without
Yes.
such
So
generality.
Q prime is here. If we define f of x to be the absolute value of x minus Q prime, which is this function, then what is written here is that f of Qi plus f of Qj, 1f, is at least f of Qi plus Qj. So this is exactly what is written here, and this follows by the convexity of this function.
In other words, you can think of Q prime equals 0.
Yeah, it doesn't matter.
And then it's.
Yes.
well, okay. If Q prime is bigger than both of them, then
Yeah,
it's
you.
the same.
So
If it's
yeah,
smaller than both of them, it's the same. If it's in the middle,
it
then
only becomes.
it's closer. They're both moving closer
Yes.
to Q prime.
So this is.
No, but in one sense, it might be interesting that here you don't use the fact that it's in that you're talking about one dimension.
Okay, so the other statement, which is also, so if we consider the sum with Qi and Qj, then on the left-hand side you have Qi minus Qj, and on the right-hand side we have 0, because they move to the same position. So we lost, so this factor, this is bigger than this by the gain. So, okay. So we played this game to bound this quantity, and then we saw that the gain in any such game is small, is at most d. So it's sort of clear. Okay.
Why is the game D not D squared?
Because you start in a position where only 2 are at 1
Ah,
and the rest are at 0.
That's really not. So I think that if you actually define the way you define things with statistical distance, that's actually not.
So there may be a factor of d here, but let's. Okay. So all of this was for the very special distributions of binomial alpha, which are very not, like really not pseudo-random. Like they are just random. Yes.
Being constant width and being regular. Are they both necessary for theoretical?
So, okay, maybe it's, I thought of saying this later, but now it's a good time as any. So here we really used regularity. So there are 2 statements about this thing. One is that we can prove a similar statement on a more general program than regular. What are these programs? There are programs that every vertex is reached with non-negligible probability, with probability at least gamma. And then this gain will be roughly 1 over gamma. So, but the proof is a bit different. It's a bit more complicated. So this is one. So this statement is true for a more general class where every vertex is either not reached at all or reached with some non-negligible probability. And the second statement is that if we take non-regular programs, then this number, the sum of the deltas, can be as large as n. For example, if you take the tribe function, which is a very simple width 3 branching program, then this gain will be like n over log n or even
This
n.
actually distinguishes between alpha and the tribe actually
Yes,
distinguishes
yeah.
between
So, yeah, and yeah, you're right. Moreover, for any constant alpha, the tribes is not fooled by this distribution. So you really need a different argument to argue about the tribes specifically.
Maybe it's a stupid question, but if you have a distribution, a branching program where you reach some vertices with negligible probability and you just erase them.
So negligible is
It has a Ripley effect. You have to define it.
Negligible, I'm assuming in n, right? Or is it in d?
so
It in D, if you want a boundary set, but you get 1 over gamma. Gamma is sort of something that is like
It's not negligible in n. You can't just.
no, it's small. It's yeah, as it's log the size of the generator will be log n times log 1 over gamma. So you have
So what you said is right, but that would recover norms
yeah.
as a generator.
I'm even less. Yeah, I'm not. Yes, but let's.
More or less, right? If it's less than 1 over, if it's less than 1 over 10n, you throw it away, and
But in this thing there are some issues. You can argue in a similar way, but you need to use some, like it's not.
It's not small enough to follow.
Yeah, I don't think it is. Yes, the tribes function. So
it's a non-regular branching program of which 3 where the gain is n.
How do you distinguish
Level
these
construction
tribes?
of something.
Can you easily show that tribes is not fooled by this kind of distribution?
yeah, so
maybe it's
But
good
maybe
to
you
write down
don't
the
want to,
definition.
but maybe.
I mean, or not.
Well, you can decide to do it later, Amir, if
Yeah.
you want. I mean, so maybe you want to show.
Yeah.
Okay, so you're going from a half
so
to the log n.
let's
But
let's
you
do it.
Half plus alpha to the log n. And so that's going to be an exponential. That's going to move you from 1 in n to 1 in n to the alpha.
Okay,
So,
so
when you have n of them, it's going to go from 50-50 to almost n.
so now we want the pseudo-random version of this distribution. And what are the pseudo-random version of this distribution? To me, it seems very natural to do the following thing. instead of having real independence, will have independence as far as the program is concerned. So what do I mean by that? So the pseudo-random version of this is that for every branching program and for every vertex in that program, so that the probability that V is reached by, so that this distribution is more than alpha, the xi plus 1. So I will write and then explain. So I'm writing concisely because there isn't much room. So I want to define the pseudo-random version of these binomial distributions. So the pseudo-random version of a binomial distribution, this will be a distribution D, will be a distribution so that for every branching program, for every vertex we choose in the branching program, in the ith layer, if the probability of hitting this vertex is more than alpha, then the next bit is alpha is close to uniform with alpha, with the parameter alpha.
Given that we arrived at,
Yeah, so it's clear the definition. For every point, the next bit is almost uniform, and there is the case where we reached a vertex that happens with small probability, but let's ignore this. So we'll not ignore it, but like for the definition, we can like throw it away.
Program, they don't have vertices like that, huh?
Regular programs, here you can write 2 to the minus d.
2 to the minus d, not 1 to d?
No, 2 to the minus d. Yes.
So the point, okay, so here I'm going to skip ahead again, but the point is that you're going to use a Nissan-like construction, except that instead of using a high-quality extractor so that everything stays uniform, you're going to take the bits that got you to V and use an extractor with a relatively large amount of noise, relatively large distance from the extracted.
So I don't know how to do this. I think what we'll do is even more similar to what Nissan did. I will explain it in a second. But you can tell me if this is what we do in your point of view when I define it. But it will be in a few minutes. So let's say that we have such a distribution. So this deals with branching programs. So we have the potential to be good. So and indeed, a random, like a small set of polynomial support will have this property. It's not hard to see. But let's assume that we have such a distribution. So I want to say that the same statement is almost true, even for pseudo-random. So I will move over the proof with this color. So all of this is just nothing. Like it didn't use anything. Here, this is OK. Here we have, instead of B, we have this distribution D. This is not so bad. But we have two cases. There are these vertices that are reached with probability more than alpha. Then this calculation holds for these vertices. So we have alpha times sum over V, probability of reaching V is more than alpha. So then we have, but on the, in the other case, we have that this probability is at most alpha. So this is at plus alpha times just the sum of the deltas But this alpha comes from the fact that the probability is small.
In any case, it's the same.
But yeah, so here, so is it clear what I wrote here? So we partition these vertices to two sets, one that are rich with high probability. They are exactly the same analysis. And there is some set here that is rich with probability at most alpha, each one. But because alpha will be a small parameter, then we don't mind losing this as well. But this equality holds, and this is at most alpha sum of delta v. So we didn't lose anything by considering such distributions.
Just look at the product of alpha IV and the probability that you reach V, then that is always at most alpha.
Alpha times the delta.
No, I mean, okay.
Yes. So, okay, so we have this thing. And now what remains is to construct this distribution. How much time? I don't have. So much time.
I think what Boaz said is that beforehand you just put an upper bound on probability of reaching V, which was 1.
Mm-hmm.
Now you're just a bit more careful, and
Yes.
when it's big you make it 1, when it's small you make it alpha.
Yes.
And the alpha IV is also at most 1, so.
Yes. So now we have to construct these objects. If we can do this, then we will be done. And like, I'm not sure how this is like. So as far as I understand the construction of Nissan or Nissan and Zuckerman, then this construction just works. So as far as I understand, but I will define some specific construction, and you can tell me, like you have more. Okay. So to define. We'll define these generators inductively using extractors. So I'll just define what is an extractor. So an extractor will be a function that gets two inputs, one of size t and one of size s, and outputs again, t bits, so t and t is the same, and it will have the following property. If we apply extractor on some variable x and the uniform distribution on s, so this will be beta close to the uniform distribution on t. Yeah, so before the parameters, the distribution of this random variable, so x will be a random variable on t bits, and this is a uniform distribution, then this will be close to uniform. And now there is a trade-off between the mean entropy of this random variable and the seed length. So beta will be something like 2 to the minus 2 to the mean entropy of x minus s. And there are constants. Let's ignore them for a second. So
it's not the mean entropy of the field. The
we want, yeah, you're right. So I will give a specific example. If x is distributed according to the following rule, we choose a uniform distribution on T, and we condition on some event, the probability of this event is at least gamma. So we chose x to be this distribution. Then the mean entropy is log 1 over gamma. So this will be the difference of, so this will be log 1 over gamma minus s.
So it's more natural maybe to write S over gamma,
if you
to
take
the minus
more-
S over gamma or something.
If you take more bits than what the information you've given, then you get back to uniform.
Yeah.
That's what they start.
So these are the extractors, and now I'll define.
I think the first time this idea appears in this format is probably the paper of Paliasa and German. Even though they use half.
So it's not the, if there is a large probability event, this is close to uniform. So now we'll use these extractor, these functions. So we'll use these things. One place that I know where they were constructed is Goldreich and Wigderson, but there are many.
But I would say
like-
Paliasa took him on it the first time that this was used in this sense.
We didn't have a good
He was the only extractor available. But that's over Haslam.
So we'll use this, and this is in a way Nissan and Zuckerman and maybe in Paliasa and Zuckerman also used it in this context before, these extractors. So how will we define the generator? So we'll define the distribution using the following functions. So let's define G0 of 1 bit to be just 1 bit. This is the starting point of our construction. We can ignore it, like it's not important. But we'll define gi plus 1 given gi in the following way. We'll get 2 bits. This will be an input. This will be of size that is the input to the previous one. And this will be of size s. S is this parameter of the extractor we have in mind. And it will be gi of x. And then we concatenate gi of the extractor of x and y. So this is the way we define, we do the construction. So it's, if you open the induction, it becomes something weird, but yeah. Yeah, okay, maybe for
This form is probably INW.
So
This is what I was saying before. The point of what you do is we needed the extractor. We needed the beta to be like 1 in polynomial n.
mm-hmm.
Okay, and that's made s log n.
Mm-hmm.
You're saying, okay, if for these regular branching programs, you'd only need the beta to be about 1 in d.
No, you need it to be 1 in log n. I will explain it. So,
okay,
but
that's going to be for the number of
yeah,
of levels
mhm,
of
yes,
recursion.
yes,
At each level,
yes.
you only need it to be
1 in D.
1
Yes.
in d, and therefore, that's the main difference.
So basically, just before so basic point, you'll have g log n. That will be the final thing, right?
Yeah. So you're right. So
your total cost is log n times the seed size.
So,
to the I. That's not clear. Yeah, very good.
so we get s times I bits. We take s
PowerPoint
times I
numbers.
bits, and we output 2 to the I bits. So the construction we'll take is g log n. Will be the output will be n. Here there will be n, and then the seed, the log of the support, will be roughly, or exactly, s times log n. So this will be, the statement is that this works. So
This works if S is log n plus log.
Yeah, so I
You
will-
have to say what.
yeah, so what does this mean in terms of parameters? This g of I is alpha I, pseudo-random binomial is pseudo-random binomial alpha I, and the important part is with alpha I, which is roughly d beta I, where log 1 over beta, where s is log 1 over beta. So it's clear what are the parameters. If we, so eventually we'll have here log n, then we'll need this beta to beat the d and the log n. For this, we need the s to be logarithmic in log n and in d. So eventually, this will be roughly log, and we will want this to be smaller than epsilon over 2d to get our previous thing. So eventually, it will give us exactly what we want. It will be, s will be log n plus log d.
No, but you wrote log 1 over beta. You said S is log 1 over beta.
Right, so he will.
Correct.
So S times log n will.
This is, s will be log n plus log d plus log 1 over epsilon. And the construction will be s times log n. So this is just a game with parameters. The point is, I think that at every step, as Russell said, we have log n steps in the construction, and in every step we lose a factor of d, sort of.
Additive. It's very important that it's additive.
Yes, it's additive. Yeah, not a factor, additive factor. So how do we prove this? We prove it by induction, as all of the previous proofs went. So for G0, it just holds. There is nothing to. This is uniform, so there is nothing to prove. And now let's do induction. So we want to argue about I plus 1. So we have our branching program, and it has 2 parts. Each part is of size 2 to the I. Together they consist 2 to the I plus 1. And now we want to argue that this property holds. So all the vertices in this side are in a branching program of smaller size. So by induction, we know that we beat them. So for V in these parts, we know it by induction. Why? Because the input to this part is exactly the previous construction. So we can ignore this, and it's the same thing. So otherwise, so this is 1, 2. We have some vertex here, V. And now we'll use the fact that it's a branching program. This is sort of another place that we must use it. We'll go over all vertices here, all the vertices U here, and see what happens. So there are two cases. If the probability according to this GI of reaching V is more than beta, then when we fix, reaching U, so U is the vertex here. If we go over all of these U's, when we fix such U, if this probability is at least beta, then the next bit, xi plus 1, given x, the whole, so we are shooting at this scenario. X given reaching U satisfies this property. So is good for extractor. So this means that the extractor of x and y is beta close to uniform on the size of x. Now we plug it into the previous construction. So now this is statistical difference. It's a very harsh test. Now we ask ourselves, what is the bias of the next bit? The bias increases by at most beta, an additive factor of beta, because this is a very, very hard test. If the bias was more than beta, then this distance will be more than beta.
Alpha plus beta, because it's also a popular vertex. You only care about...
No, I conditioned on this.
You condition only on the U. You are now looking at some
Yes.
that is in the middle.
But I have the induction in mind. Like
now the right part of the branching program is another branching program.
Right.
It's written there. So GI fools it. So if you feed it instead of uniform X, something that's beta close to uniform on X, you get another beta to your error. That's all.
I thought you don't want to just fool the... I thought you just want to fool it, or you want to
No, it's using
show
that's
this
a definition.
PR bin.
Yeah, that's right. So that's a definition.
So you are
So
you're
whatever
looking,
was true.
you're looking at PR bin and
so
just says that for
every
popular
V.
popular
So now
vertices it should be closed. He's
right,
saying
right.
for every vertex
So
it's
you're looking
closed.
so you have to look at some V in the middle that is kind of popular.
no, there is no popularity test. So the statement is as follows. We fix this U, condition the distribution of fixing this U, on hitting this U. Now, what is the bias condition on this of the next bit after B? The
After
bias
V.
of the next bit after V, condition on U, is at most the previous bias plus beta. This is because this statistical distance is at most beta.
No, I mean if reaching V is it doesn't matter because I think anyway your definition allowed it, but if reaching V is very unlikely, then that test is
See, the test has to be you reach V and you
Right.
leave with a 1 rather than...
Yes.
right. But
Okay.
if V is
So
popular,
the
then that's
difference
okay.
between those two is less than beta.
Yes.
But yeah, as
But-
saying if you're looking at the conditional
Yeah.
probability given that you've reached V,
Yes.
then you're
And
dividing by
anyway,
a small...
I guess that's why you need. I mean, that's why it's
But,
important that this definition only talks about popular Vs.
yeah. But it does, so
Yes.
we can go on.
Yes. Yes.
Okay. So we have this, and on the other hand, if the probability of reaching U is less than beta, then the whole thing contributes to the total bias at most beta. So now we look at this vertex. We look on the bias of this vertex. So if we are reaching such a vertex on the way, then the bit is alpha I plus beta close to 1/2. And there is a chance that we don't reach a vertex that happens with probability at most beta. So if we happen to do this, let's assume that the bias is always 1. Like we always miss it by far. But even in this case, the next bit, when we average over these u's, has small bias.
Increases the bias. But
Yeah, by a small amount.
I think the point is that you don't care about popularity. All you say that, you know, to the right part of the branching program, when you feed it not a uniform X, but you feed it almost uniform X, because you are this conditioning, then the definition there changed. The definition of pseudo-randomness changed by adding to alpha I, whatever it was, adding beta on both of them.
Yes.
That's all. Even the definition of popularity changed, but they don't care. I mean, and since eventually you will define the alpha to be the log n times.
But why do you need all? I mean, now I'm just confused. I mean, why do you? I mean, this analysis is so general. Why couldn't you just, without talking about, you know, being unpredictable and all that, just show that the distribution of the final layer is constant statistical distance to the output? I mean, where does
So
it fail?
at some
Why do you need this next bit predictability?
At some
condition?
point, you will need to use this quantity. You will need to define this quantity on the branching program.
Why?
So, okay. So
I mean,
I'll try to explain. Let's just a second. So how do we argue about this? How did Nissan argue about this? There is a quantity that decreases with branching programs. What is this quantity? Its length. So the length here is 2 to the I, the length here is 2 to the I plus 1. And by induction, we sort of argue that the error is upper bounded by this quantity that increases at every step. If we want to get something that is smaller than n, eventually, so the length at the end is n, this will give us the log n factor. If we want to reach at something that is smaller than n, we must use a different measure on upper bounding this error. We must use by induction a different upper bound on the error. And this upper bound, as far as we know how to do, maybe there are different ways, is this quantity.
They are not using a bound on the statistical distance from what the uniform does on the layers of the branching program. They avoid it completely. That's how they avoid the union bound on anything.
I mean,
They are just, using this induction, they are just bounding the various alpha i's in the definition of pseudo-random for different lengths to the I program.
So you think of it as we're doing this. Okay, think of it as just going from G0 to G1. Okay, and you're doing that you're taking T steps, every T steps, and combining it into every 2 T steps, and you're combining it into T plus a C. Okay, so you're really doing this n over 2t times, and each one is close to the uniform is beta close to the uniform distribution. But now you have to say that the concatenation, actually, but you could do it that way, because you don't really have to do this kind of complicated induction on the levels. You just have to do an induction. You just have to do it sort of bottom up. So you take blocks of size t, you pair them up, and you replace the independence with the extractor. Now,
This is exactly the hybrid argument.
Once you go beyond a block, okay, so you don't want to add up you introduce beta every, and what this argument is showing though is that beta error every block, since it's a regular thing, the error doesn't add up over n over t blocks.
yes.
It still, even cumulatively, reaches only beta d.
So the crucial point, I guess, in the argument was that when you looked at these U's in the middle, you didn't want to argue that they are close to what would happen in the uniform distribution.
No, you don't care what they are.
That's the crucial point. That you didn't.
You don't.
You don't care that it's whether it's close to the uniform distribution or not.
Definitely not.
You just look at
The construction
whether
of
they're popular in your distribution.
But
That's
But-
but
but
you could
then
have
once
sort
you-
of say this
once
as
you
well.
do that, you could use, you could say, you could use,
I mean, there will be because
just as in the
Yeah,
induction
so-
assumption. So you could only use this, what you did on the top, on the bottom level, on each bottom level. You're going saying here's a construction that halves the number of random bits we use, okay, and keeps it regular and
I'm not sure.
okay. And so the construction is take your randomness, divide it into blocks of size t, pair up the blocks of size t, and introduce a random seed and define the next block of size t to be the extractor with that one seed of the previous block of size t. That has, that one layer sort of obviously has your property that you want, okay, without doing this kind of middle argument. Okay. So
I'm not sure that I followed what you said. I'm sure that I didn't follow. What I want to go back to what I started with. You can argue all of this by take this construction, use this measure, and just it works by induction, exactly like the argument that Nissan did. But this quantity for me seems, if you just plug it in, seems not informative, at least to me. Maybe someone else sees it. But if you ask this question, which
It was asked explicitly. In fact, the fact that distributions like this, like what we call pseudorandom alpha, can be generated in logn and log+logn bit, was known, and it was asked whether they fool. I think Salil Badan and maybe Eyal Rosenman. Anyway, just this alpha that you can generate them in logn and log+logn steps, whether they fool. What do they fool? In fact, whether they fool log space is if alpha is one over polygon.
So this is one point, and the other is a tribes function. So I just want to comment about it because this sort of shows that this will not work as is for general branching programs.
So the tribes function doesn't work for your original
Even
of the alpha.
yes.
But does that mean that the extractor construction doesn't, that there is an extractor that doesn't pull it? Or that
It will be a very strange proof. Maybe I don't know.
No, I mean, it's maybe not so strange. I mean, you have to find a contrived extractor that basically gives out this,
bias,
this
slightly
bias
biased.
distribution. Maybe it is.
So what the example I want to say is that if we take this binomial alpha, the true one, no pseudorandom, and the alpha is, say, 10 over log n, so this is 10 or 100, I don't know, then the statistical difference between tribes of binomial alpha and tribes of u is at least 0.01, I don't know, something like this.
It's going to be like a
Yeah, so so it depends. So there is a so the point is that as long as alpha is not 1 over log, it must be sub-constant as a function of n, where before it was a constant, then it doesn't work. It cannot work. This is the point. And this is sort of very simple to see. It's a very simple calculation. What is the tribes function? So the tribes is a O of ends. So I'll draw a picture. There are K tribes. So each person belongs to a tribe, and the person's like it's a partition of our voting power. Each tribe is of size T. And for a decision to accept a decision, we have that there is some tribe that all of its members agree. So it's end of O of xij with the scaling so that this function will be balanced. So you can choose parameter t and k so that this number will be the probability that this is 1 is roughly 1/2.
All of ends or all of ends or
Or of ends.
It's symmetric, but
And now, yeah, as I defined. And now if each one in the tribe changes its mind with 1/logn probability, then the probability of a tribe to say 1 increases by a constant factor. So it becomes like, instead of 1/2 to the t, it becomes 1 minus 2, 1/2 plus alpha to the t. So this t is logarithmic, and if alpha is 1/logn, it changes it significantly. Now, because we have, so it's a very simple calculation. I will not do it, but I will. But this statement is true. So this proof cannot work for every branching program. And I think an interesting question. So for alpha smaller than 1/logn, it does work. And then I think an interesting question is to find the correct way to argue, maybe in this way, maybe in a different way, on just the tribe's function. Like, I don't know how to do it.
Follow the tribe.
Yes.
Generally, it's not known that if you go to bin alpha, forget about pseudorandom bin, or go to bin alpha for alpha less than 1/logn, we don't know whether or not it falls bounded with branching program or not.
Yeah, if alpha is smaller than 1/logn, I don't. Yeah.
It might fall even non-regular ones.
Yeah, I don't have any example of this.
Do you have any statement in terms of the influence of the Boolean functions computed at the end?
I don't, but
Tribe seems to be the function which has
Mhm.
large influence variables, right?
well, yeah. So you're saying implicitly that that they have. You're saying if you replace the variables probability 1/2 by 1/2 plus alpha, that it doesn't change the outcomes very much. So
yes.
that means that you're saying basically that all
Yeah, you're,
all functions
Mhm.
computed here have low average sensitivity.
yes, this is true. Yes,
Even low max.
Low max
Yeah.
sense.
Low max.
yes, yes.
Well, it's over a uniform
So
distribution.
that's why
I
I
don't know
think
about
you
max
get the D
sensitivity.
there rather than something else. Probably.
Again?
The theorem about the sum of the delta V is
Ah,
bounded
mhm.
by D.
Mm-hmm.
It seems like it can be replaced by the maximum influence.
Yeah, maybe you're right. Yes. So it was clear, I hope.
Yeah.
So thank you.
No questions.
So for tribes, just to make sure, we don't have any construction for tribes.
I don't know. Yeah, I don't know of any construction, or even I don't have a conjectured argument, like a heuristic argument. That's,
So you don't know to full. I mean, you know that bin alpha, the non-pseudorandom version, does full tribes,
yes.
but you don't know that the pseudorandom version fools.
So it depends maybe how you define pseudo-random. Yeah, I don't know how to do it.
What about the possibility that even with constant alpha it fools regular branching programs of constant alpha?
No, so this is true.
No, regular.
So this is true. We just don't know.
Constant alpha.
This is true. Alpha is epsilon over d. So we just don't know how to.
Generate.
Yeah, we don't know how to generate.
One
Yes.
with logarithmic.
Yeah. Yes. Maybe it's a good point that their alpha for our purposes we think of epsilon and d as constant, and their alpha is constant, and we do this in some intuitive way should translate to a polynomial size construction, but we do not know how to construct a pseudo-random thing with constant alpha. We just know how to do it with 1 over log n alpha. Like we can distinguish between these two sort of things.
Conjecture construction for constant alpha with polynomial.
I don't know. I don't have.
Ran is one of the authors. There is a paper of Feingold and Raz where they, in the case that you have a distribution, a random walk on a graph where you know the probability that every vertex, which is the case here, you know what the probability is of essentially now.
Yeah, you have a lower bound on the probability.
But the pseudo-random generators that don't, that somehow they save on the seed length at every. They recycle the available entropy for later extractor uses. So I don't know if maybe in this case you could.
Also I mean, slightly different, but in Treisen, Wallen, and Rheingold, if you know the stationary distribution of the walk, then you can.
Yeah, I don't think it's the same idea. If you know the stationary distribution of the walk. The Rheingold is a problem.
Although, so the stationary distribution here is supported just on the. It's like.
No, but at every but even at every step.
Yeah. So. It's it's.
Because of the starting point. Maybe it's good.
So thank you very much.